going to try to have the exams graded by Tuesday. I told the TAs to please have them graded by Tuesday, so hopefully we'll have them back on Tuesday for you. Still have a couple students who need to take the exam, so I can't actually talk about it yet. Today, we're going to finish up talking about DLists. Just a few more comments about them, and then we get into what probably is the hardest topic that you will encounter this semester, which is recursion. I know pointers have been problematic for many of you, but recursion is also something that seems to be conceptually difficult and takes practice to get used to. So it will be the last kind of major concept that you are introduced to in programming. So in 102, you were introduced to, the basic stuff: variables, assignment statements, arithmetic operators, if-then-else statements, Boolean and relational operators, loops, functions, and here you've been introduced to pointers, and recursion is the last major topic you will be, or concept in programming you'll be introduced to. The rest of it is just kind of building on the data structures like arrays and objects and pointers, recursion that you've been taught for the rest of your programming careers. Okay, so let's first finish up talking about doubly linked lists, which you will be implementing in Lab 8. So essentially, this whole API that you see here, you'll be implementing in Lab 8. So he doesn't give you the code for a DList. He does give some code for using them, which we did not go through last time. So he has duplicated much of the DList interface that you get with a STL list, but he's not doing the so-called operator overloading with plus plus or the asterisk. So if you want to get values out of his DList, you have to do it in a slightly different way. So here he has his example with creating a list and then reversing the list. So with his DList, you create a DList object and you're able to point to the individual nodes in his DList. And if you remember, he's using a circular list. So his first node, in some sense, is a Sentinel node, and it's circular, so it points back. And so that's what your list, doubly linked list, looks like for him. And when you do this, so you might have give him 6. So the push front is simply adding things to the front of the list. Okay, so when you do push front, you're simply adding them to the front of the list. So you could be either what two operations, well, you could do insert before give, or you could do insert after the Sentinel node. Both of those will insert into the front of the list. And then here, his lBegin is returning a pointer to the first node in the list. And you can access the element by directly accessing the field. And the reason is he declared the elements of his D node to be public. If you go back and look here, you can see he declared his D node member functions to be, I'm sorry, member variables to be public. Okay, and then he accesses and prints out the first one, which was give, and then he uses the flink to advance D to the next location and prints out him, uses flink to advance D to the next location and prints out 6, uses the flink to advance D to the next location, which is back here, so now D points to the Sentinel node, and that's exactly what L.end returns is the Sentinel node, a pointer to the Sentinel node, so at that point the iteration ends and we're done. Okay, so questions about that. By the way, I know this is assuming that actually the original words in the list had been 6, him, and give. I know it's, so just in case later you're looking at it and said Dr. van der Zanden said it was reversing the list, this is assuming the words were given to you in the order 6, him, and give. Because then push front would push 6 first, then him, and then give. Okay? So questions about that? Okay. Okay, and here's another example where instead of iterating through the list, he was actually always looking at the first element. So he's saying while not empty, he's retrieving the first element because L.begin returns a pointer to the first element of the list. So I know this can kind of give some of you difficulty when you're combining stuff like this. So think of this a bit like a mathematical expression. So you know if you have 6 times 3 plus 4, it evaluates the 6 times 3 first to get 18. Then you add 4. It's kind of the same thing here. It first evaluates this expression, L.begin. And that returns a pointer to a D node. So now you kind of have a D node pointer after you evaluate that. And when you say now arrow, that dereferences this D node pointer and gives you access to one of the fields in a D node. So you kind of have to get used to this notation where you're combining a couple operations in one stroke. Okay, and then here, after printing S, he then deletes or erases the first node in the list. So there's a couple examples. And then he's giving you some hints on how to set up the list. So in the constructor, what you're going to have to do, so in the constructor for a DList, you have to allocate a Sentinel node. Okay, so the Sentinel node is just one of your DList nodes, and you need to make the flink and blink so you need to make the flink and blink pointers point to the Sentinel node. So the Sentinel node points to itself initially because the list is empty. And you have to set the list size to 0. Okay, so that's what you need to do in the constructor. So even at the beginning, you have to set up a circular list. So this is circular. Okay, it's empty, but the sent node points to itself because there is no other node in the list, and it points back to itself because there's no other element in the list. So that's what you have to do in your constructor. Allocate a sent node, make both its flink and DLinked pointers point to it. And then with insertion, okay, so if we are inserting before some node, in this case we're inserting before Eileen because D is our so-called target node. So insert before is giving us a value, and then the node that we're inserting before. And my recommendation when you do insertion is to define another variable called, say, previous node that points to the node before D. So previous node is essentially, well, I'll let you figure it out, but it helps to define another pointer called previous node. And then, of course, you'll have to create a new D node, which you'll point to, say, using another pointer, maybe new node. So you'll set S to be equal to on in this case. And then you need to set 4 pointers. Okay. You need to make the new node's flink point to D. You need to make its B-link point to what? If you're going to be putting new node into this list before D, what does its blink need to point to? Previous node. So this is where it helps to have previous node because you can just set the B-link pointer to previous node. And what else? What other 2 pointers need to be set in order to get it into the list? Okay, so what? For come needs to be set to what? On. Very good. So the flink for come, which is the previous node, needs to be made to point to new node. And one more pointer. Blink for Eileen, which is D, has to point back. So if we look at what pointers, there's 4 new pointers. Okay, 2 emanating from new node, 1 from D going backwards, and 1 from previous node going forward. So you'll be setting 4 pointers in your list to get it in there. And, as he indicates, once you have insert before, you can actually use insert before to implement insert after, push front, and push back. Okay, I'm not going to go through all of them for you. Let you figure it out a bit for yourself. But as an example, push front is really insert before on the first node in the list. So when you do your implementations, you really only need to implement insert before, and then your remaining 3 inserts can be done by calling insert before using an appropriate target node. Okay, and I'll let you figure out how to do insert after and insert back. So questions about insert before. Okay. And then the last one deletion. I want to delete, so with deletion, you're again given a pointer to the node you want to delete. So you're going to be deleting this node. But remember, you can't delete it immediately. Before you do that, you need to rearrange some pointers. And again, I suggest that you define 2 additional variables for the node that goes before and after. You can call them before node and after node if you want. I'm calling it previous node and successor node. And you're going to have to rearrange the links for these 2. So what 2 links need to be modified here? Yes. Very good. Very good. So previous node F-link and successor node B-link need to be modified. So previous node F-link needs to go to Eileen now because on is being deleted, and Eileen needs to point back now to come because on is being deleted. So you need to do these 2 operations first, and then the last thing you can do is to delete the node. So 1 and 2 is rearrange pointers. And 3 is delete the node. Okay, so with 1, you're resetting previous node's link, and here you're resetting successor node's link. So those are the basic operations: the constructor, the insert before, the deletion. The iterators returning pointers to nodes is pretty easy. They're 1-line operations. You also have to remember, you also have to decrement the size. Okay, and as we discussed last time, what's nice about a Sentinel node is there's no special cases on the boundaries. It's because you have the Sentinel node in a circular list, inserting at the beginning of the list or inserting at the end of the list is no different than inserting into the middle of the list. All you're doing when you're inserting at the beginning of the list, which is right here, is inserting after the Sentinel node. And when you insert at the end of the list, you're inserting before the Sentinel node. But in those cases, the Sentinel node is still part of the list. It's still a node in the list. So you can treat it like any other node of the list for insertion or deletion purposes. Yes?
So with the, like list.end and like list.reverseEnd, it would just be that one Sentinel node?
Yes. Exactly. So that's a great question. So list.begin and list.end and list.rn both return a pointer to the same Sentinel node. And the only difference is that when you're iterating in reverse, you use the B-link pointer. And when you're iterating forward, you're going to use the F-link pointer. Okay. And it's kind of up to, unlike with the STL where you actually distinguish between a forward iterator and a reverse iterator, you don't really do that here so much, meaning you have a node And then it's up to you to say, do I want to go forward using the F-link pointer, or do I want to go backwards using the B-link pointer? Whereas with the STL, when you had an iterator, it was typed. If it was a forward iterator and you said plus plus, it advanced you using the F-link. And if it was a reverse iterator and you said plus plus, it went that way. So you didn't have as much control. Dr. Planck's code kind of gives you a little more control to move forward or backwards as your heart desires. Okay. Other questions? Okay. So, and the destructor, he just, word of warning, you have to make sure you go through it and deallocate each node in the list. So if you had these 4 nodes, the Sentinel node, and then each of these 3, you'd need to delete all 4. And just one word of caution, in the destructor, delete the Sentinel node last. So delete all, I'll call them regular nodes first. And delete the Sentinel node last. Okay, can anyone tell me why it might be disastrous if the first thing you do is delete the Sentinel node? You don't know then where the list ends. Very good. So first thing I do, remember the way we know, we have a circular list. So the way we know to stop is when we reach the Sentinel node. So if the first thing we do is blow away our landmark, we'll have no way of knowing when to stop. So we don't think of the Sentinel node as our landmark or a lighthouse. The last thing we do is delete it. So questions about DLists. Okay. One last thing, because I can say this based on something that Senia told me during the exam. Some of you, when you are, let's say we have D node, and we have, say, begin, we'll say DList begin. So we want to return, in this case, a pointer to the Sentinel node. Not the Sentinel node, the first item in the list. So the first item in the list, in this case, is going to be Sentinel flank. Okay, that's the first item in the list. Now, yesterday on the exam, this is the right way to return it. Okay, because flank is a dnode pointer. If you look at flank, it is a dnode pointer. Okay, that its type matches this type. But on the exam yesterday, some of you were putting an asterisk in front of it and having trouble with getting it to compile. And the reason you're having trouble getting it to compile is when you put an asterisk before it, it dereferenced it. And instead of returning a pointer to that node, it tried to return the node itself, which is not right. This is returning a pointer. It's not returning an actual D node. So you have to get used to the difference between just returning a pointer and returning the value of the object to which the pointer points. So we wanted a pointer returned in the list problem yesterday. We didn't want the list itself returned, which is what you were trying to do when you dereferenced the pointer. So without the dereference, you're returning a pointer. With the dereference, you're returning the value to which the pointer points, and that's not what is desired. Okay? Again, it's a practice thing, so you just kind of have to get used to, either making the mistake and then also hearing the TA or me say, hey, it's a mistake. This is how you do things. Okay? Okay. So, moving on, recursion. Hey, the book gave its example of recursion, which was mowing a lawn. I'm going to give my own example of recursion. You have an enormous pot of coins. Okay? And I've flunked, well, I didn't flunk art, but certainly the grade I got in art was a testament to the art teacher's, shall we say, appreciation for persistence in the face of incompetence. So that is my, I've always been thankful that the world rewards mathematical talent and not artistic talent, because I would be in bad shape and probably unemployed if it rewarded artistic talent, but fortunately it rewards my mathematical talent too. Okay, so those are coins. Obviously not very many coins, but let's say I gave you a huge stack of coins and I told you that your life depended on giving me an exact count on the number of coins in under a minute. Okay? And you're trembling because you can't possibly count all those coins in 1 minute. However, you're surrounded by friends, and your friends are willing to help. So what you do is you dump the bag of coins out, and you divide them up into a bunch of piles. Okay, and it turns out you're really popular. So you're able to divide it out among 100 friends. And it turns out that when you divide it among 100 friends, the piles are small enough that they can count them all up in 45 seconds. Okay? Why just 45 seconds? Well, you need the remaining 15 seconds to ask them, hey, how many there, and add them all up. Okay? So the idea, this is the idea behind recursion, which is you take an enormous task and you divide it into a set of similar tasks, identical tasks, that are smaller, and then you do a recombination, some kind of combining operation that combines the results from the smaller task to get your final answer. So here, the idea was I divided the counting into, I divided all the coins into a bunch of smaller piles, but everyone performed the same task then. Everyone was still counting, same task you would have done, okay, but you just distributed it. And then the recombination was querying each person and adding up all the values to get your final result, okay? And let's say that the task was so gigantic that when you did it, your friend, maybe you got 5 minutes, and it turned out that each of your friends, when given the pile, it was still too big. Their pile was still too big. They might have in turn called in their friends and further subdivided their pile. Okay? So, but the idea, the final idea behind recursion is at some point, the problem gets small enough that you can solve it without further subdividing. So in this case, eventually the pile of coins got small enough that you could count them in less than a minute. Okay, or in the lawn mowing example, it was mow the front lawn and mow the back lawn. And then it was mow the left side and mow the right side, but eventually it got down to a specific instruction, which was go, mow left to right until you finish that part of the lawn. So there's kind of these 3 elements to a recursion. Okay, so the first element, and unfortunately neither the book nor the Dr. Planck's notes present it this way. But the first thing is you need to be able to subdivide a task into smaller but otherwise identical tasks. So it's the same technique that you would use to solve the larger task you use for the smaller tasks. Okay, then there is the notion that when the task is small enough, you can solve it. And this is called the base case. Okay, so you'll often hear in recursion something referred to as the base case. That's where the subdivision stops, where the problem is small enough that you can solve it. And then 3, you recombine, or you combine actually, combine the results from each of the subtasks to get the final result. So in our case, the recombination involved adding the results from each of the subtasks, the number of coins from each of the subtasks. So that is what recursion is, fundamentally. We need to subdivide a task into a smaller but otherwise identical task. Okay? Another example that the book gives you is binary search. If you remember from 102, with binary search, you had an array, and the items in it were sorted. And what you did was you looked at the middle element. Let's say we're searching for 15. Okay? So you looked at the middle element. If the key matched the middle element, you returned that index. If it was less than the middle element, you performed the search on the bottom half. And if it was greater than it, you performed it on the upper half. But this was kind of the same idea, that you did the identical operation then on the remaining half. Okay, so again, you looked at the middle element, which in this case is 1. And in this case, it's equal, so you return 1. But the idea was you essentially performed the same task on an array that was half the size. And at each step, you threw away half the array and repeated the task on an array that was half the size. And you stopped when either the key was equal to the element at that location, or when was the other thing when you stopped? Okay, but how would you know you couldn't find it? Okay, but there's still, okay, I'm trying to get at, how do you know that it's not in there? How do you know when to stop? Like in a DList, we knew to stop when... That's right. So you're keeping 2 indices, high and you were keeping low. And when they crossed over, you knew that, when they crossed over, you knew you couldn't do it anymore. With binary search, we'll stop the same thing. We'll essentially be passing in 2 parameters, a low and a high. And we will know when to stop when low is equal to high, because then we know we've reduced it to an array of 1 element. So if we get down to where we're considering an array with only one element, it's either there or it's not, right? It's kind of like herding animals into a pen, and you finally get them there, and you know it's either there or it's not. So that's the base case, is where you get down to an array that has only one element. Okay? That's your base case. Okay? Here's another example. I just think it helps to have a number of examples. Okay? Let's say I want to sort a bunch. Yes, go ahead.
So why not use a full loop and a bunch of if statements?
Pardon? So you can, and in fact, the question is, why not just use a loop and a bunch of if statements rather than recursion? And the answer is oftentimes you can use a loop rather than recursion, and oftentimes the loop is faster. But there are times when recursion allows you to solve a problem much more elegantly or easily than you could with recursion. So Dr. Planck's notes actually solved the Tower of Hanoi problem, which I think is a little too complicated for today. But solving the Tower of Hanoi problem without recursion is brutal. Okay? It's actually very difficult, almost it's very hard to do with only a loop. Same thing in lab 9, you'll be doing a game. So actually, this is another example where recursion often comes into play, is with games. Okay, so many of you have played checkers or chess, or at least know how to play checkers or chess. Okay, so think about how you might play a game. So you start out with checkers, and let's say chess. Okay, so you're white, and there's a whole bunch of moves you can make as white to start a game. You can move a pawn, you can move 8 pawns or 2 knights. I think you can make 10 moves. Okay? So then you often, if you're playing, you think about each of these moves. Well, now you have to think about what are black's counter moves. Well, black initially also has counter moves to each of your moves. And then you can counter with your own moves. And then black can counter. So it turns out that when computers are asked to play a game, what they do is they use recursion to think about how to play. So they consider a whole lot of positions before they make a move. And the way they do it is they in turn, they basically say, okay, make move, say pawn to E. I know it's not done like this, but say pawn from E4 to E6. And then they need to figure out, okay, if I move from pawn E4 to E6, now it's the same game except it's a different chessboard, right? So they apply the same reasoning starting at that point. But at some point, they have to backtrack, right? They can't, you don't just go down one path indefinitely. You have to come back up and consider other moves. This would be really hard to do with a loop, but it's really easy to do with recursion, it turns out. Okay, so while binary search is possible to easily do with a loop rather than recursively, it's actually difficult to do this kind of analysis of a chess position with loops. Okay, and the reason is at any one point you have to kind of, when you backtrack, you've got to backtrack, which means you have to move pieces back to where they started. And recursion makes it easy, it turns out, to move pieces back to where they started, whereas a loop doesn't. With a loop, you have to explicitly keep some storage about where things were. It'll become clearer when we show you how recursion is implemented. Okay? So here's a couple more examples with recursion where it's real helpful. I have a group of numbers, 83, 71, 62, 105, 201, 305, 54. I tell you to sort these numbers. Okay? Well, it turns out we showed you two algorithms in CS102, but neither of them were really efficient. It turns out that the most efficient way to sort a set of numbers is to pick an arbitrary number in your set. We'll arbitrarily pick the first one. And to divide the numbers into those numbers less than 83 and those numbers greater than 83. So we can see that 71, 62, and 54 are less than 83, and 105, 201, and 305 are greater than 83. So what we do is our task is we are going to perform the same task, which is sorting. But what I'm going to do is, in effect, choose two of you and say, okay, one of you, Charles, I'm going to have you sort all the numbers less than 83. And I'm going to say, Kelsey, you sort all the numbers greater than 83. So I'm dividing it into two tasks. And then Kelsey, you may decide, hey, I can sort these numbers just by looking at them. And Charles, you may also decide you can sort them by just looking at them, which the two of you can. And in fact, you probably find it a lot easier to sort those three numbers than to sort all seven by just looking at them. But you may decide if it was bigger that you would further subdivide. So you could conceivably say, okay, I'm going to subdivide to my two friends. So you might say all numbers less than 71, which are 62 and 54, I'll let one of my friends sort, and all numbers greater than 71, which is the empty set, they get off easy, I'll let them sort. And then, of course, you insert the number, which is called the pivot, in the middle. So here, the identical task is we're going to sort two collections of objects, one that's less than the pivot and one greater than the pivot. The recombination is to put the set less than the pivot to the left, put the pivot in the middle, and put all numbers greater than the pivot to the right. But when we come back, we know that the left side is sorted and the right side is sorted. Therefore, by putting the pivot in the middle, everything is sorted. Okay, and the base case is when you get down to a point where there are so few numbers that you can easily sort them. Okay, one obvious thing is getting down to where there's a single number, because obviously a single number is sorted. Another thing that's done in computers is that maybe when you get down to, say, 20 or 30 items, you actually might use selection or insertion sort, because at that point they actually become faster than doing recursion. But at any rate, at some point you get down to a base case where you have so few numbers that you can efficiently sort them without further subdividing. Okay? So all of my examples so far have involved basically dividing a task in two. Okay? There are examples where you don't divide a task quite in two. One of them is factorial. So n factorial is often written as n times n minus 1 factorial. And you're told that 0 factorial is equal to 1. Okay? Well, here, the recursion isn't dividing it in two. The recursion is actually creating a problem one smaller than the original. And the recombination operation is to multiply that result by n. So the recombination is the multiplication operation. Okay, the smaller task in this case is just one smaller. It's n minus 1 factorial, but it's the same task. In the base case, we can stop when we get to 0 factorial. Okay, so we know how to solve 0 factorial. We know that that is 1. Okay, so there's an example where we didn't divide it in half. We actually just made it one smaller. Okay, for those of you who like math, this is often called a recurrence relation. You'll see this more in your computer science careers, but it's a recurrence relation because it doesn't give you an exact formula for calculating n factorial or it doesn't give you a closed expression. Instead, it gives you a recurrence. Okay? Now, if I were to program this up, so this particular recursion, I might write int factorial, which I'll abbreviate fact, int n. Say if n equals 0, return 1, else return n times fact n minus 1. Now, I probably also should add an if n less than 0, return something, because factorial is undefined for negative numbers. So I really shouldn't. What happens if n is, well, you haven't yet been told. I'll show you in a moment what happens if n happens to be less than 0. But you can see that my recursive, this is called a recursive function. It has the base case, which stops the recursion. So if n is 0, I know how to compute the result. Otherwise, I have the break and recombine. Break into, well, this is the smaller step. And this is the recombine. But this is a what we call a recursive call. So the function is calling itself. Okay, so we call that a recursive call. Okay, and it doesn't just, you could have multiple recursive calls. Okay, so in my sort, I'm not going to write it all out, but in my sort that I had, I basically took an array, call it A, and essentially what I did was I said choose a pivot. So I in effect said pivot. Well, first of all, I might say if A's size equal 1, return, because with the size of 1, it's already sorted. Okay, otherwise, I might set the pivot. I know that it's at least size 1, so I set the pivot to be A of 0. Okay, I might then say for each element in A from 1 to n minus 1, if A sub I is less than pivot, put A of I in array low, else put A of I in array high. Then I would call sort on array, on low array, or array low. and I would call sort on array high, and I'll just say return, actually, return. So, a second. I'll say array low equals sort, array high equals sort, and then return an array that consists of array low, the pivot, and array high. Okay, again, that's pseudocode, but you get the idea that what I'm doing, I'm making two recursive calls right here to sort, and then this is my recombination step. And this is my base case. Okay, and this is just setting up. So this is dividing the task. But there again, I'd be making two calls to sort, two recursive calls. So this is an example where I've made two recursive calls. Yes?
Is there any way in programming that you can have both those called at the same time?
Yes. So the question is there any way in programming that you could have them both called at one time? On your computer, not really. But on a parallel computer, then or a multi-core, there might be a way to do it where you assign each of the two tasks to a different core. And then as long as they don't have to communicate with each other, which they don't here, they could do it in parallel. So that's what I was doing with the coin counting example to save my life, is actually I was doing it in parallel. Okay? So the other advantage of recursion is that oftentimes by subdividing it into similar tasks, I can actually put the tasks on different computers or different cores and run them in parallel, and I can get the solution faster than if I ran them sequentially. Okay? And back to your question with a loop, it's much harder to parallelize a loop than it is to parallelize recursion. So another advantage of recursion is that you can often parallelize the tasks and do them simultaneously. But that's not a subject for this course. We have a course called 462 Parallel Computing where they talk about exactly how you do that. Okay. Yes, Bentley.
Okay, so it says if a size was 1 return, that's just the regular return thing.
Yeah, actually it should have been return A because I was having returns everywhere. So probably it was better to say return A. And remember, you can't actually return an array from a C function or a C++ function. That's one thing you can't do. So actually what I'm hiding from you is something that's in this for loop. You're really not creating two new arrays. You're actually juggling elements in the same array. You're actually doing something where if your pivot's 33 and this is 81 and this is 21, what you're really doing is moving 21 over to here and you're moving 81 over to there. So you're actually doing some in-place exchanges in the same array, but I'm hiding that because it's too complicated. I don't want you worry about this in 302. I'm just giving you the general gist of how that sort is done. By the way, it's called a quick sort. So I'm just giving you the gist of how it's done, not actually the implementation details. Okay? So questions about recursion, about this idea of dividing a task into smaller but similar tasks, the idea of a base case that when the task gets small enough you can solve it, and the idea that you may have some kind of recombination operation at the end. That's the three basic things of recursion. Okay, so why is it so important? Why is the base case important? Or let me go back here and, whoops, to my factorial. So what happens if I have a negative number in my factorial? What happens if I call factorial and I call it with fact of minus 5? You get what in effect is like an infinite loop, although it's called an infinite recursion, because fact minus 5 will call what? Fact of minus 6, which we'll call fact of minus 7, and obviously we're never going to get to n equals 0. So this is going to cause an infinite loop, not an infinite loop, an infinite recursion. Okay? And what happens, well, you still don't know what happens. I haven't told you the rest of the story, but I have to show you how it's implemented. It's going to turn out that we're going to run out of stack space. Okay? So let's talk about what happens in the computer. Okay? So we start out, let's say we actually start out with a call to fact3. The computer actually, fact3 maybe gets called from main. Okay, so remember their stack frames. So main has, so we have our stack, and at the bottom of it, there's a stack frame for main. Okay, so main, maybe at line, it's line 1, line 2, whoops. So main calls fact3. It has some, maybe it has I equals 5, so maybe main is int I. Maybe we do a cin for I. Then maybe we're saying print factorial of I, and I know again this is pseudocode. So this is line 1, this is line 2, this is line 3. So main stack frame keeps track of the value of I. And then it calls factorial. So factorial had n, if you remember. So this call to factorial has n3, and it also remembers that the call to main came at line 3. So it remembers where main was when it called main. Okay, and our call for fact, this was int fact int n if n equals 0, return 1, else return n times fact of n minus 1. So this is line 1, 2, 3, and 4. Okay, so fact of n with n3 now says is n equals 0? No. Else return n times fact of n minus 1. So it actually pushes a new stack frame for factorial. N is 2. And it remembers that it has to return to line 4. So when it's done, it needs to return to line 4. Now this factorial does the same thing. It ends up calling another version of factorial, so it pushes another stack frame. And it also remembers that it has to return at line 4. And finally, the last call pushes on another one with n0. But this one now returns. It says n is equal to 0. Whoops, it also knows that it has to return at line 4. So n is equal to 0, so it returns 1, and it pops this stack frame. But it knows from this, I crossed it out, but it knows it needs to return to line 4 here. So now it comes back to this stack frame and resumes execution at line 4. The return value is 1. N is equal to 1. So it returns 1. The return is 1. And I go back to the previous factorial at line 4. Okay, so I pick up execution at line 4. Again, my return value is 1. But now n is equal to 2, so I'm now multiplying 2 times 1. Hence, I return 2. I need to pick up execution at line 4. So I return 2 here. The new value of n is what? Down here, what's the value of n? 3. So we end up returning 6 to main, which picks up at line 3. So line 3 prints fact of I, the return value is 6, so it prints 6. So you can see that what the computer is doing is creating a new stack frame for each call to factorial. So each stack frame has its own copy of the parameter n. And that stops n from getting overwritten. Because when we return to factorial, we need to remember what our own private version of n was. So each stack frame or each call to factorial has its own stack frame which stores its own value for its parameters. And we don't lose those values when we call ourselves recursively. And the other thing you can see with a stack frame is it needs to keep an indicator that indicates what line it should return to in the calling function. We need to know where to resume execution in the calling function. So one of the things a stack frame also keeps is the line number to which it should return in the calling function. It contains some other information as well, but this is important, kind of important that you remember it. A stack frame, some of the information it keeps, not all, because it keeps more, but it keeps track of your parameters. So copies of parameters. Copies of local variables, and conceptually, the line number in the calling function that should be executed when this function returns. So those are 3 important pieces of information that a stack frame keeps. So now you can see what happens when we get into an infinite recursion with factorial. We keep adding stack frames to the stack, but there's a finite amount of memory in a computer, and so eventually we run out of memory and the program is terminated, and this is caught. So we can actually try programming it up and see what happens. Okay, so there's our program, right? So let's compile it. So we'll run it on 5, that's 120. We'll run it on 0. That didn't work out so well. Okay, we'll run it on -10.
You didn't program the command line.
Oh, you're right, sorry. Okay, 0, that worked out well. I was wondering why it didn't actually work. Okay, and now we'll do -10, and it segfaults eventually. Actually pretty fast. Now let's just have fun. Factorial of 50, whoops. Zero. What do you think happened? Arithmetic overflow. Turns out that 50 factorial is an incredibly large number, and you can't represent it. Let's see, 15, whoops. I know, that's good. 16 is good. Is 16 good? That doesn't look right. No, it's actually already gone. Do we really think, look at the numbers for fact 15 and fact 16. Is that right? Pardon, what?
5 times 5 is not 6. So 15 times 15.
Yep, so that doesn't look right. Okay, certainly at 17 we see it going off the tracks. So what's happening is arithmetic overflow.
You started as an unsigned integer, but
Let's do it.
we get it.
Yep, we can because we'll get an extra bit. It won't give us much, but it'll give us something. So fact 6, whoops, I just keep wanting to do it as a command line. Okay, see if we get anything more. So it worked for 17. So we got one more. But we didn't get it for 18. So it only saved you for about one time before it. It makes sense. You only get one extra bit, and we're multiplying by more than 2. So you'd only expect it to really survive one more time. So at any rate, you have to be careful with these things. That's why on the Kino lab, lab 6, you had to be careful with canceling out your terms because factorial grows wickedly fast and it quickly overflows. Okay, so do we understand how recursion is implemented using stack frames and why it's so important also to have that base case to stop an infinite recursion? So just like you can get infinite loops, you can get infinite recursions. You have to be careful that you have a base case because the base case stops the recursion. And you also have to be careful to check for any illegitimate values. So here, I really needed to add something that said if n is less than 0, do something. Maybe it's return -1. Maybe it is make a C error. You gave me a negative number. Okay, something to deal with that case.
Would you want to do one for if say they gave you a number bigger than you can calculate?
That's harder because oftentimes the code is portable, and what's going to cause overflow on my machine might not cause overflow on a 64-bit or a 128-bit machine. So I can't actually hard code that fact. So there are certain things in life that, okay, the answer is yes if it's beyond the scope of this course, but you could actually each time check to see how big the number is, and you could kind of figure out doing a check whether you're about to overflow or not. But it requires more sophistication than we have. You have to first of all be able to check how many bits are in a, which you can do, but we haven't talked about how. And it gets complicated. So don't worry about that. Just assume they don't do something like that. Okay. One last thing, and I'll let you all go. So recursion can be very elegant, but it can also be very dangerous. So another common operation is Fibonacci numbers. A beautiful recursion is the Fibonacci numbers. So the Fibonacci numbers, fib of 0 is 1, fib of 1 is 1. They're not always, sometimes there's slight differences in how they're defined, but we'll say fib of 0 is 1, fib of 1 is 1. If n is greater than 1, then fib of n is fib of n minus 1 plus fib of n minus 2. So the numbers are essentially 1, 1, 2, 3, 5, 8, 13, 21, so on and so forth. And here's a very simple program for calculating a Fibonacci number. Okay? Well, you run it and it works fine, as he says, for small values of n. It returns very quickly. Okay? But if you try to run it on fib 40, so let's do that, and then I'll wrap up. So I'll put this into my even though it's fact, I know I called it fact, but whatever. It's now fib. And so I run it on 6, and we're back very fast. I run it on 40. Whoops. Da, da, da. Ooh, that ran pretty fast. Okay, fact 80. Da, 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 da. Very slow. In fact, you could be here probably until tomorrow and it would not finish. Surprising? Yes. But what's going on is that each call is, so this one is actually calculating fib of n minus 3 plus fib of n minus 4. And this one is calculating fib of n minus 2 plus fib of n minus 3. It's kind of branching into a tree. Okay? This tree is blowing up exponentially, like 2 to the something power. Okay? It's not quite as bad when it's 80. It's not quite as bad as 2 to the 80, but it's close. 2 to the 80 is a huge number. So you have to be careful because recursion is very seductive this way, but we're doing a lot of repeated computation, right? Fib of n minus 3 is a repeated computation. Fib of n minus 2 is a repeated computation. So in this case, we could do it much more quickly with a loop. Okay, because I'll go into that. It's too complicated for this right now. I'll go into it on Tuesday. And on Tuesday, we're going to go into a more complicated example with recursion. It would behoove you to show up on Tuesday, because if you don't show up on Tuesday, the chances that you'll do lab 9 are essentially 0. Okay? So lab 9 is very heavily based on on the example that we do on Tuesday.